So in this question, we want to deal with um, this term. So I want to minimize this expression right here. So first of all, we can think about the whole thing inside as just a simple denotion of a, which is actually a function of x. So in this case, like depends on x. This matrix have different eigenvalues. So basically, what we have right now, it's we know that the norm, the matrix norm, is actually equals to the singular value of a, which is actually the squared the maximum singular value of a, which is actually the squared of maximum eigenvalue of a transpose a. So now I want to define our problem as semi-definite programming. So first we need to know that we want to minimize such t. So basically the t here, it's actually act like a barrier. So t should be greater or equal than all the eigenvalue of a transpose a. So in that case, t squared will be greater than or equal to lambda to lambda a transpose a, which when you minimize it, it will become actually the lambda, the maximum lambda. So the t we get eventually will be the result we want to find. So and then how you're gonna represent such all of these conditions using semi-definite programming, right? So what we need to do here is we define such function, such matrix. We can simply prove that if this matrix will have an eigenvalue of t lambda 1, t minus lambda 1, and t minus lambda 2 of the matrix A transpose A. Actually, I want to correct myself from before. It's actually the minimum. It will be the square root, because right now we're dealing with all the condition of it's dealing with t squared. So here I have some mistakes. So it's like t squared and t squared. Therefore, just think about like when you need to get the eigenvalue. You used this is exactly what we get from the question before this question in the lecture slides. So in this case, so we can simply just say we want this matrix to be positive definite. Therefore, all of his eigenvalues will be positive. So t squared will be greater than all of the eigenvalues right here. Therefore, we can write the constraint like this, and then the t eventually we get will be this value right here. And then we can actually rewrite the whole thing differently by the lemma. So here in this case, this is our constraint right here. We divide the whole thing by t, which is a scalar, so we can do that. And then we move this t inside here. So this is supposed to be r minus 1, r very inverse. So this will be the actual r right here. And then this will be the p, and this will be q transpose, and this will be regular q. So also we should notice that if here we don't need to have the constraint of t greater than 0, greater or equal than 0, because we're dealing with t squared. But in this case, if this matrix is actually positive definite, then the trace of it will be all positive. And what is the trace of it? The trace is 2t. And if 2t will be greater than 0, then you don't need to write it again. So yeah, this is the constraint, the alternative constraint.